A small introduction about Sir. So Sir has obtained his bachelor degree in Electronics and Communication Engineering from Delhi College of Engineering. As of now, it is known as Delhi Technical University in the year of 2003. He then moved to Kyushu Institute of Technology, Japan, to pursue his master's and PhD. A PhD under the guidance of Professor Casey Kaneto of Department of Biological Function and Engineering at Kyushu Institute of Technology. After finishing his PhD degree in March 2009, from April 2009 to November 2010, he worked as a scientific researcher at Nanosystems Integration Laboratory at Research Institute of Electronics, Shizuoka University, Japan, where he worked on MOSFET based on single electron transistor devices. His interest in the area of organic electronics ranges from device applications, organic field transistors, organic solar cells, and organic light emitting diodes to the study of charge carriers transport or photocarrier generation in various organic materials. Since November 2010, he joined as an assistant professor in the Department of Electrical Engineering at IIT Indore. Later, in June 2006, he was appointed as an associate professor in the Department of Electrical Engineering at IIT Indore itself, and in February, he was appointed as a professor in the Department of Electrical Engineering at IIT Indore. Lately, his research interest includes nanostructural growth of oxide semiconductors, nanoparticle synthesis, pulse laser ablation, local surface plasmon response, hydrothermal and solvent techniques, hydrophotodetectors, and photoconductive devices. He also expanded his horizon towards piezoelectric generators, energy harvesting devices, and biosensors as well. He has successfully guided 12 PhD students under him, and 5 more are presently pursuing their research work under his guidance. He has additionally guided several master and bestseller students as well. Some of his articles have been in the journal Highlight and their view graphs included in cover page of the journal. His research group has twice been awarded as Best Technology Development and Best Research Paper Award of the Institute. Professor Vipul Singh Sir has authored 120 peer-reviewed international journal papers and 130 plus conferences papers. He has been on the review board of several international journals, conferences, and some of committees of DST. He has also served as the head of the Department of Electrical Engineering, Associated Dean of Academic Affairs, and JEE Advanced Chairman in past, and presently is serving as the Dean of Academic Affairs at IIT Indore. So, welcome once again, sir, and we are very blessed to have you here. And now I am handing over the session to Professor Vipul Singh, sir, and he will be delivering his talk on organic semiconductor. Sir. Okay.
So first of all, good morning all of you. So I'll be today talking on. When I was first contacted, I was told that I can give a talk on organic electronics. So of course the topic is little broad. So I'll be talking on organic semiconducting materials and devices. Mainly the current trends and future prospects. I will be covering and give you a glimpse of what all activities we have been doing as far as organic research is concerned. But before I go into the research part, just I'll take some time to make because I guess the audience is sort of mixed. So I'll also take some time to give you some brief introduction about organic electronics in general, what it is and what prospects it holds. And then towards the end, I would finish on a note by going to the future prospects, where we are and where we are likely to go in the near future. So that would be the brief flow of thought process as we go through the presentation. So before I move, I would just like to mention, so in a talk like this, I always am very excited to introduce my research group. I joined IIT Indore in 2010, and as was introduced, so and I founded this molecular and nanoelectronics research group, which basically is focused on. So if you see the conventional electronics, it is all high temperature based processing techniques are involved, and you have mostly dealing with rigid substrates. So in a philosophical way, I just try to put it. So we are trying to move the fabrication part of the electronics from dry and hard towards soft materials, and using some wet technologies as well. So of course, it's an interdisciplinary field. As you can see, it involves a bit of chemistry, a lot of physics, and device physics especially. So all these things come at the interplay, and then of course, as you go on, and once you have the device with you, you would like to integrate the device and develop some kind of integrated system. So that is the whole idea or the theme on which we are working from the beginning. And the advantages of molecular electronics or organic electronics, if I say, there are some distinct advantages. The first is the cost of fabrication of these devices is very, very small compared to the conventional counterparts. Of course, the other very important aspect that is there is they are scalable to large area. So in typical applications which require us to develop systems or devices which can perform over a larger area. So for that purpose also they are well suited. They are also well suited for some kind of disposable and flexible electronics. I'll talk about flexible electronics towards the end of the talk. And that is where the advantages are, and these are different themes that are undergoing in my research group. So we work on research and development of organic field effect transistors, organic photosensitive transistors. These transistors actually respond to the light stimulus. We also are interested in some kind of basic studies to understand how the photocarriers are generated inside these materials, and how we can harvest effectively when we excite these materials by light. Then we are also interested in R&D of some kind of inorganic, organic hybrid photodetectors, where we try to utilize the best of both worlds. So if you see, conventionally, the electronics has developed from the point of view of silicon, and in the case of silicon, what happens is the material as such is rigid, and the cost of fabrication. So when we started fabricating devices using silicon-based technologies, we were having a lot of bulk material, and as time progressed, we have moved on the scaling trend. That is what is known as the Moore's law, and we have adopted what typically is known as the top-down approach. So we have been scaling down these devices over the years, and that has been going on for close to 5 to 6 decades now. So of course, if we compare with that, these technologies are much cheaper, but of course they are not going to replace silicon. So I'll talk about that part also. So it is going to augment some of the existing things, and in some, especially some very niche applications, these materials can replace silicon. But of course, silicon will not be replaced in the mainstream, as it holds a lot of other advantages compared to these materials. And I'll come on to that part also. We also do a lot of hydrothermal growth of oxide-based semiconductors. We utilize these materials for developing some kind of biosensors based on conductive polymer and zinc oxide. And we also use them for studying some kind of surface plasmon resonance effect, especially in metal nanoparticle decorated nanostructures. So that is broadly all the research activities. Well, it is not listing out all. We also work on several other aspects as well, like piezoelectric and triboelectric nanogenerators, which we have been developing, which is mainly for the purpose of energy harvesting. And these are the basically the detailed view graphs and some of the things that we are. Lately, we have been very much interested in developing UV photo detectors. There are a lot of applications involving UV photo detectors, and at present, this is one of the very important focus area of our research group. And we are also developing some kind of flexible electrodes additionally besides the already told themes. So we are developing some electrode materials which can be flexible in nature and therefore are suitable, ideally suitable for developing flexible electronics. So this is my research group. All these students have passed. This is a long ago old picture. So I have close to 12 students have finished their PhD. At present, one postdoctoral fellow and 4 PhD students are there, and two MS and one MTech student working in my group. And we have got funding from DST and then ISRO and some other funding agencies. DST, AMT, DST Fast Track, and DST Bilateral, DST JSPS. Recently, this DST CRG project is also undergoing. So these are the various funding agencies from where we have got support. And now I'll come on to the today's talk. So this is the broad presentation outline of my talk today. So I'll first, give you a slight motivation behind organic electronics. Why we are interested in the very first place, because it is very important to understand what is so special about organic electronics. And then we'll talk about some very basic things like the bonding in these molecular materials. I'll also discuss about organic semiconductors, their materials as well as their properties. And I would also like to discuss briefly about some kind of classification of these materials broadly that is well understood, and also different coating techniques by which we can actually form thin films of these semiconducting materials. And then based on that, I'll move towards what kind of charge transport happens in these materials and how it is different from the conventional charge transport that happens in inorganic semiconductors, like silicon. So whenever I say inorganic, it is mainly meant with silicon. But of course, you can have other inorganic semiconductors as well. And then finally, I'll spend some considerable time on, especially on organic field effect transistors, and little bit I'll talk about some kind of hybrid photodetectors. So today's talk is mainly going to focus on organic field effect transistors and some kind of other photosensitive devices. So first is motivation behind the organic electronics. So the why we are interested in organic compounds. So if you see carbon, its atomic number is 6, and it has a very unique position in the periodic table. And because it has 4 electrons in its outermost shell, so that makes it very advantageous because it can form a lot of bonds, covalent bonds with neighboring carbon atoms, and this property of carbon is known as catenation, we all know. So basically, that results in these kind of wide variety of molecules that can be formed using carbon-based compounds. Now, if you see, these are some kind of small molecules, or they are small, not in the sense, I mean, when we compare with respect to large molecule like polymer, so of course they are small molecules because they have certain number of carbon atoms. In typically in a polymer, you may have a large number of carbon atoms because this monomer unit itself might be repeating over like 100 or 200 monomers constitute to make a polymer. So that is polymer, and typically polymer we classify it as a macromolecule, and so as we go, as we go from monomers to polymers, and then we further move ahead, then we see these biological systems, the DNA strands, and things like that. So these DNAs and the amino acids and other biological molecules that we often come across are also long chain organic compounds. Okay, so if you see the nature by design, whatever living organisms you see around you, plants, animals, they are all carbon based, and typically the hierarchy that nature follows is also based on carbon. So that is one of the reasons why we are interested in carbon and carbon based electronics. And the other I would come on to eventually. So basically, using carbon-based materials, not only we can introduce a lot of new functionalities or attributes into the devices that we develop, but eventually we can also think of electronics which can be. There are people research groups working, so they are trying to make it biodegradable. So if your electronics, once its lifetime is over, you can actually bury it in the soil and it gets degraded over time. So that is where all this goes. So it has its own, advantages. So if you see, all living things are designed using carbon, and therefore, organic electronics or a lot of interest in the organic materials there. Now I'll just come to the pi conjugated organic semiconductors. So the Nobel Prize for the discovery of conducting polymers was given in 2000, in the year 2000, to these three scientists, Professor Alan J. Heeger, Professor McDermott, and Professor Shirakawa from Japan. So they jointly shared this Nobel Prize, and it was for the discovery of conducting polymers. So if you see, historically, polymer means, or what was understood out of polymer is, it's a insulating material, it's a plastic, right? So that was the notion that everyone used to carry till 1977, when this was a very big accidental discovery actually. So this polyacetylene, this is the molecule polyacetylene. Polyacetylene, it's thin film they were developing for certain some other work, which accidentally was annealed at a temperature higher than what it was supposed to be by the student, and what turned out to be was a Nobel Prize. Okay, so the student actually accidentally annealed the thin film of these material at a higher temperature than that was required, and it actually led to change of the, if you have little bit background in organic chemistry, we all have studied in plus two. So what happened is, from cis isomer it changed into trans isomer. Cis isomer of this polymer was actually insulating in nature, but when it turned into trans, it was found to be conducting, and that's where their interest rose, and they tried to investigate. And these two people were chemists, he was physicist, and finally he gave the theoretical explanation using the Hamiltonian approach to clear out why this would behave as a semiconductor. So that was the discovery. And what is meant by pi conjugate? So pi conjugation is basically where you have alternate single and double bonds over a long chain. Okay, so that is one of the essential requirements. If a material, if any organic material is supposed to behave as a semiconductor, it must have this kind of pi conjugation. So must have alternate double and single bonds along the chain. Okay, now if you see here this pi conjugation is broken. Okay, so as the longer it goes, the more delocalization of electron takes place, and that results in that has a direct impact on the band gap and other related things. So basically, this is just to show you. So typically, carbon will have p orbitals, and it is these lateral overlap of the p orbitals that results in delocalization of the electrons over the backbone of the molecule. Okay, and that results in these kind of interesting structures. And that is what is basically pi conjugation. And I'll just also discuss here a little bit about the different types of features of organic semiconducting materials. So of course they have a lot of advantages, as I mentioned. You have unlimited material design option. So one thing I would also like to emphasize, unlike the the conventional inorganic semiconductors. Inorganic semiconductors, right from the molecule itself, right from the material aspect itself, you can start and play around a lot. You can tune the material properties, you can change the structure of the molecule and things like that, and see how does it impact on your overall performance. Besides that, you have different types of morphologies possible. You can do a lot of band gap engineering, and the band gap engineering, if you are aware, it directly would impact your overall device performance. If you are developing a photosensitive device, or if you are developing a transistor or a LED or solar cell, in all these cases, if you alter the band gap, you will get the distinct changes in the properties and also in the behavior of the devices. These are also lightweight and flexible and also sort of inexpensive. And you can have electronic as well as ionic transport is also possible, which typically happens in natural systems. Okay, in nature, all your communication happens. So if we touch a hot object, immediately we are able to sense. So if I'm touching a hot object, the layer of my skin comes in contact, and it generates a impulse signal which is sent to my brain, and then my brain directs my hand, or that's a sort of a reflex action, that okay, I need to move away from this. This is hot, right? And all this takes a very small amount of time. There is almost very small reaction time. So all this is happening through the signals that are generated. There is no silicon being used in our body. It's all completely organic system. So the neurons transmit the signal to the brain, and the brain again redirects it, and through your nerves, the signal is transmitted to brain, and brain again redirects it back to your muscles, and muscles also are having some kind of biological, basically some kind of organic reaction is there through which a muscle actually actuates. So that is also going on. So all this thing takes place, and that too in a small fraction of time. So that is also another beauty. You can have electronic as well as ionic transport. That is the another advantage is the excitons. I'll come on to that. What is an exciton? So excitons are highly localized here. On the disadvantage side, we have a little bit of disadvantage also with organic semiconductors. We have, for the device engineering, of course, vertical integration is quite challenging compared to, like, you have vertical integration possible in the case of silicon. So that is much more challenging with organic devices. And of course, there are some challenges with respect to their stability and lifetime, but many of these issues are now getting sort of resolved. So besides this, if you are using organic materials, so suppose if my sensor is based on organic material, but the interface electronics is based on conventional silicon-based chips. So then there is organic inorganic interface that comes into play. So those things are also to be looked at. And one of the major disadvantages is they are having a lot of disorder. So disorder plays to its advantage. You have highly localized exciton, and it also is sort of a disadvantage because you have highly localized charge carriers. That means the charge carriers in these materials are highly localized, and that leads to reduced mobilities. I'll come on to what I mean by reduced mobility. So this is basically the scale at which, if I try to put things up, so and how ordering happens in most of the things that we know. So, for example, if you see, this is a amorphous, completely amorphous kind of material, and then if you move on to if you have at least unidirectional alignment, then you have a laminar structure, then you get nanocrystalline materials, further improved alignment, then you can get microcrystalline and highly crystalline materials. So of course these are basic examples of how the crystallinity or the orderness in the system or in the material helps in realizing different types of structures. And then this is also on the below scale. It is showing the different scales at which typically you can observe these kind of behaviors. Now, let me come on to some of the applications. So, the applications that we talk of course, as I said just now in the previous slide, the mobilities in these materials are less. So, you cannot, think of developing a microprocessor or a front-end processor using organic materials. But on the contrary, since mobilities are less, you can always, of course, look for applications which do not require high mobility. For example, displays. So you can have printed displays, you can have printed solar cell. Solar cells typically do not require high speed. It is simply a device meant for harvesting the sunlight, the energy present in sunlight and convert it into electrical energy. You can think of solid state lighting applications. This is again very important, and recently, if you see, we have moved from the era of the tungsten bulb, filament-based bulb to CFL to fluorescent lamps in CFL, and now we are going towards LED. And of course, one of the applications of organic devices is also to have large, area-based LEDs, which can give white light illumination or white light. They can emit white light. And let me tell you this: the way we see things coming in the future, you will have a complete ceiling, complete ceiling emitting white light all across, and that too will be done by a very thin sheet. It will be like a wallpaper. So you can put it up and you can light it, and it will run at a very nominal power. So all these things are possible. You can have printed sensors. You can also think of printed RFID tags as we go towards Internet of Things. One of the important aspects is RFID tags. So you need to tag several of the items, and therefore you require your tagging technology to be cost effective, and that is where again organic electronics has to play a role. Besides this, of course, more recently there have been also interest, and people have demonstrated some kind of flexible, e-paper. So you can have the paper can actually be also a display. You can have a flexible display like this, and again in times to come you will have a completely flexible rollable television in your home. This is not a very distant future. So this is going to come. Similarly, you can also think of some kind of tags which are put on edible food items, which actually are able to tell what is the how much percentage has perished over time and things like that. So especially for poultry and poultry related products. And then you can also think of electronic skin, electronic nose. You are able to use these kind of systems to distinguish between different vapors, and that could be volatile organic compounds or your oxidizing or reducing gases. So that's where gas sensing comes into play. You can also think of integrating these devices in your wearables. That is what we talk about as smart fabrics. And of course, organic solar cells is anyway there. So if you see, the march towards organic electronics has been like this. So if I look at the size versus year and trying to put it all on one graph. So basically we started from the era of vacuum tubes, we have moved to transistors, integrated circuits, VLSI, and then if you extrapolate this, we are going towards now molecules. And the way things work in molecular electronics, so basically the entire approach is not sort of top-down approach, rather bottom-up approach. Okay, so you try to build your electronics from starting from the smallest entity, that is a molecule, and trying to sort of aggregate these molecules to develop different things, and then so that is what this slide is about. We have been following top-down, scaling approach in the case of conventional silicon-based electronics, whereas molecular electronics offers a totally new approach, which we call as bottom-up approach, and we try to, realize systems which are maybe at par or in some cases working better than their counterpart. So wherever your mobility, and mobility, let me tell you, mobility has a critical role to play when your device has to switch very fast. Okay, so mobility, that's why we are always having there is always that kind of this thing is there, that we should have a high mobility material. High mobility is mainly meant to, ensure that the material is able to switch. So if you want your material to perform well at high frequencies, it has to switch quickly, and that is where high mobility is important. But of course, these materials do not offer that high mobility, but they have a lot of other important things associated with them, which are sort of advantages, and that is where all these converge. Next is the structural properties and applications. So I'll just give you a glimpse of. So these are some of the very conventional, different types of polymers and some other materials that are there. So like polyacetylene, this was the discovery in 1977. Then we have come across a lot of different types of polymers. This is called polyparaphenylene ETP. Then this is polyparaphenylene vinylene PPV. Then we have now derivatives of this, and then the thiophene family. So this is thiophene family. Compared to this, if you see, this is the benzene ring. In this, you have a heterocyclic ring. Sulfur atom is also sitting in between. So this is a heterocyclic ring, which forms the monomer or the basic unit. And then when it repeats, it forms a polymer of thiophene. And then you can actually have an alkyl group attached at the at the two position. So that is basically leading to poly 3 alkyl thiophene. And then you have other sort of polymers like polypyrrole and polyfluorine and various other. Now these days, more of donor acceptor type polymers have also come into play, and a lot of people are interested in DMOITs kind of polymers, which are giving better performance. These are some little older examples. And if you see, the one of the important advantages which conjugated polymers offer is that you can tune their conductivity, and the conductivity can be changed or modulated from that of insulators to the level of metals. So you have a full spectrum. You can tune their conductivity by means of doping, and the way we do doping in these materials is little different than the way we do it in the inorganic semiconductors. But nevertheless, once these materials are doped, you can actually modulate their conductivities by several orders of magnitude, and that is again one interesting thing. Then if you see, they conventionally conducting polymers ever since their discovery, they have been used in a lot of applications, starting from electrostatic discharge protection, metallization. They have also been involved in lithography, corrosion protection of metals. Then devices, of course, are there, OLEDs, transistors, and solar cells. They have also been used in electromagnetic interference shielding, and also for the purpose of interconnect wiring, etc. Can I move this board? Mm. So these are basically overview of some of the potential applications involving use of conducting polymers. So I'll just, since maybe for some of you this would be a very new or totally very different topic, so I'll just briefly take you through the molecular materials as such. What is the basis? So the basis of when we talk of molecular materials, of course, the molecular orbital theory comes into picture, and in this, the electrons in a molecule that are basically there in a molecule, they form molecular orbitals which have different energies and shapes. And as the atoms, atoms have electrons, same is the case with molecules. So different atoms have different atomic orbitals, and with these atomic orbitals leads to the basically these atomic orbitals lead to the formation of molecular orbitals, and typically these molecular orbitals they spread over the entire molecule, and of course there are some drawbacks also with respect to the MO theory, but anyway we are not going into details of that. So I'll come on to basically the formation of molecular orbitals. So you might have studied a little bit about molecular orbital theory in your plus two, but I'll just skip this part. Maybe I'll just take you to the understanding part of it. So, suppose you have one molecule. So basically, this is the nuclei of one molecule, and with each molecule you have a wave function associated with it, and these are the atomic wave functions. So just like we have two, suppose you have two atoms, and they have their own atomic wave functions associated with them, and when they are brought in close proximity of each other, it leads to some kind of constructive, or it can lead to destructive interference. Constructive when the positive side of the atomic wave function or positive of the atomic wave function adds up with the positive of the neighboring nuclei, then that leads to this kind of reinforcement of the overall wave function, and that is what is sort of constructive interference. And in case if the negative positive of this, positive amplitude of this, and negative amplitude of the neighboring nuclei wave function, they overlap, then that leads to a null at the point exactly in between, and that is what is termed as the node. So this point is called as the node, where the probability of finding an electron is zero. And this is how you have the destructive interference coming into play. And I'll just take you through some of the conventional discussions that you might have done at plus two, but it all starts from there. So I would also like to emphasize here that if you look at any conventional semiconductor material, whether it is silicon, zinc oxide, gallium arsenide, or any other material. So typically, when we are talking about semiconductor material, it's the atomic orbitals and the atoms that are essentially coming into play, and the periodic arrangement of atoms leads to formation of bands. Okay, so it's the periodicity and the crystal structure that is very important, but the basic participating entity is atom when we talk of inorganic semiconductors. In the case of organic semiconductors, it's actually not the atom, but because these are basically molecular materials, it's the molecules which are the basic participating entity, and based on that, we look at the overall kind of structure the band structure that comes out. So I'll just talk about how band formation takes place in a while, but this is just to show you. So if you have, let's say, two isolated hydrogen atoms, so if they subtract each other, that is what we call as anti-bonding molecular orbital, if you recall. And if they have a constructive interference, that is 1s of this and 1s of this, they interfere constructively with each other. That is the positive of the atomic wave functions of the two atoms that come together to form a hydrogen molecule. If there is a constructive interference, then you have this kind of molecular orbital coming up, and that is called sigma 1s, and this one is called sigma star 1s. And typically, bonding molecular orbitals have a lower energy, and anti-bonding molecular orbitals tend to have higher energy, and this forms the basis of emergence of band structures also in these materials. So this is what is explained on an energy scale, and in fact we can calculate what is called as the bond order. So bond order is roughly half of the total number of electrons in the in the molecular orbital minus total number of electrons in the anti-bonding molecular orbital. So if you see here in the bonding one you have two electrons, and in the anti-bonding you are having zero. So you had started with one electron each each of these hydrogen atoms. When they combine, so it forms sigma 1s, that is bonding molecular orbital, and you have the bond order as 1. So since the bond order is 1, H2 is more stable than its separate atoms. Okay, now if we think of different types of molecular orbitals, so you can think of drawing different types of MO diagrams with respect to to relate the energies of molecular orbitals to the atomic orbitals from which they are derived, and if the total energy of electrons is lower than that of the molecular orbitals, the molecule formation is typically favored. So that is the underlying concept. And the total energy of electrons is lower using the atomic orbitals, and therefore formation of molecule is not favored. If the total energy is lower than the lower using the atomic orbitals than the molecular orbitals, then of course the formation of molecular orbital is not favored. And you can get the idea of this by simply calculating the bond order. Now, typically, once the molecular orbitals are formed, they can actually, combine with each other, and that is what is called as the linear combination of atomic orbitals or the orbitals, and basically using which we can think of the delocalization taking place over the entire molecule. And the filling of molecular orbitals, the same rule applies. First, you fill the sigma, that is the bonding molecular orbital. Pauli's exclusion principle is also applicable, and Wundt's rule is also typically applicable. So this is just showing some kind of combination of orbitals, what is allowed, what is not allowed, and things like that. So you have this is the lateral overlap of two p orbitals side by side. This is the side by side overlap of a p and a s orbital, and of course the sideways overlap of a p and a s orbital is not allowed. So this is not allowed, while this is allowed. So you need to keep that in mind. Now, just I will give you a slight idea about. Of course, I'm not going into too much of details, but if you are interested, you can refer to some kind of textbooks on these topics. But just I would like to emphasize on two important points here. So the combination of two or more p atomic orbitals or any atomic orbitals to afford two pi molecular orbitals can be described by simple mathematical relationships. So this is the pi star and the pi. That is your pi energy level and the pi star. Basically, typically your anti-bonding molecular orbital and bonding molecular orbital. So what I am trying to suggest is they are formed by the linear combination of the wave functions associated with respect to the molecules to which they belong or the participating molecules. And then comes the anti-bonding molecular orbitals. So typically they result from destructive interference, like I mentioned, and you have reduced electron density in between the nuclei, and they tend to destabilize molecule. And higher in energy, they are typically higher in energy than the bonding molecular orbitals at the same time. And most important thing is once you calculate the bond order, which is half of the number of bonding electrons minus the number of anti-bonding electrons, you can tell a lot of things. So if bond order comes out to be greater than zero, then the molecule is more stable than the separate atoms. If bond order is zero, then there is a zero probability of bond formation, and the greater bond order, the stronger is the bond. This is a typical molecule formation of heteronuclear molecule. So here two participating nucleus are different in nature. One is a hydrogen atom and one is a fluorine atom. So fluorine has 7 electrons in its 2p orbital. So these electrons, combine with 1s and form these kind of, the bonding molecular orbital, that is sigma MO, and non-bonding molecular orbitals. which are typically formed when the formation of HF takes place. And as you can see, the AOs, that is the atomic orbitals, are not at the same energy level in case of dissimilar atoms, because fluorine is more electronegative in nature, so the energy levels of these would be different. So the higher Z effective of F results in lower energies of its atomic orbitals. Now, okay, I'll just try to maybe little bit skip this part and come to. So basically, this is the diagram is for the molecule ethine. Okay, how the bonding and the anti-bonding molecular orbitals emerge. So what I'm trying to suggest is, as we bring molecules close to each other, these energy levels split into anti-bonding molecular orbital and bonding molecular orbital, and that is where the emergence of band structure takes place. So basically, in molecular materials also, the arrangement and the close proximity in which these molecules are being placed with each other would determine the extent to which my band gap is going to be. And that is one of the very important handle actually in our hands to tune the band gap in these materials and use it for our advantage. And this is the same being described. I will just skip this. May I come to the okay.
Sir, can I ask you one question here? So here, we have already studied about the semiconductor devices like silicon and all. So there, EK diagram we used to draw energy versus the distance diagram we used to draw. And valence band conduction band, difference between valence band and conduction band, that is the band gap. So accordingly, the characteristics of the particular semiconductor will be different. Now here, since you are saying that the phenomenon is not in the atomic space, it is in the molecular space. And you are saying that its bonding energy level is a bit less compared to the anti-bonding energy less. Can you compare the bonding energy level in the valence band side and anti-bonding?
I will just, I'm about to come to that point. So just give me 2 minutes and I will come. Okay, so basically, now I come back to the pi conjugated system. So with these few examples of ethine and some other simple molecules, what I've tried to show you is, as we bring these different molecules in close proximity of each other, we can have these splitting of energy taking place, splitting up of energy level, and once the molecule is formed, and that energy level splitting results in the formation of what we call as the bonding and the anti-bonding molecular orbital. Now, this is for one molecule, and now you have several such molecules. When we talk of a thin film, okay, because whenever we talk of devices, typically we will have a thin film which will be the active region of the device, and in the case of that thin film, you will have several such molecules which will come in close proximity of each other. So that is where the not just the energy levels with respect to this molecule alone, but the influence of the neighboring molecule on these energy levels starts or begins to play a role. Just like you have atom and another atom placed in close proximity begins to extend its influence on the electron associated with the atom number one, the atom at the atom number two, its nucleus begins to extend its influence on the electrons of atom 1, not just the atom nucleus of atom 1. So same is the case here as well, as these molecules come in close proximity. So the only difference between these set of materials and the inorganic counterparts is that typically here the basic entity that is building up the material is molecule and not atoms. So that is the fundamental difference. And molecule in itself can have several atoms, as we are aware, as I showed in the initial diagram. So in a monomer itself, you can have several atoms, like chlorophyll is a molecule. Okay, chlorophyll is a molecule, hemoglobin is a molecule. So all these are molecules, right? So you have several carbon atoms, some other atoms as well present in these molecules. So it is not simply an atom, and these are the basic building blocks, and that's why there is a distinct nomenclature being adopted to represent what is called as conduction band and valence band in conventional semiconductors. So the valence band, what we call as the valence band in the conventional semiconductor, is basically called as the homo level. That is the highest occupied molecular orbital, and the lowest unoccupied molecular orbital LUMO is typically the conduction band. So you can, for the sake of understanding, you can bear this in mind that LUMO corresponds to conduction band in, just like you have conduction band in inorganic semiconductors, we have LUMO here, and just like you have valence band in inorganic semiconductors, you have HOMO as the molecular energy level. But the main purpose of this distinct nomenclature is to emphasize on the point that these emergence of these bands is taking place because you have molecules participating and not atoms. Okay, so that is a very important thing. And then there are some other important aspects as well. In these kind of materials, it's the weak van der Waals forces that are also playing their role, and then the dielectric constant of the medium, which results in this kind of uh, homolumo level formation. Okay. So I'll again come on to that point in a while. So that is where we are going towards. So basically, as I said, pi conjugation is basically this kind of single and double bond extending over a long range that can lead to pi conjugation. And with pi conjugation, what is happening is the sideways overlap of the p orbital results in delocalization of electron, and the larger this delocalization goes on, the better it is for the homolumo levels, and it has a direct impact on your final band formation. So with this example, probably it will become much more clear. So this is a 1,3-butadiene. So this is 1,3-butadiene. As the name suggests, you have two double bonds at 1 and 3 position. So this is 1,3-butadiene, and what happens is the sideways overlap of these pi orbitals leads to delocalization of electrons over the entire. So this type of molecule shows two different resonating structures, and that is what is being shown here. And then what we are trying to do is, so the blue ones and the red ones are the positive and the negative of the atomic wave functions associated with these p orbitals, and we look for when all of them are in phase, when two are in one direction and the other two are in another direction, and likewise all sorts of possibilities. Okay, and if we try to look into all these possibilities, so we find that the zero node, that is when all the four overlap with the constructive interference taking place, so that results in lowest energy level. Then this one will have little higher energy than this one. Then this one will have even higher, and this one there is no overlap. Then there is all in destructive interference taking place. So you have node here, you have node here, you have node here. So there are three nodes here. You have here one node and two nodes. Only two nodes here. Here also you have one node, and here zero node. Okay. So based on that, the energy levels will be like this, and typically the electrons will occupy the first lowest energy levels, and it is this gap that it refers to. So try to understand this is just the story of one butadiene molecule, and then several such molecules come together, these energy levels also tend to overlap with each other slightly, and that results in the formation of the homolumo levels, okay, and the band gap. And that's where it is very important to understand that by playing with the molecular structure itself of the molecule, we can tune the band gap. So the highest filled molecular orbital is here, lowest unfilled molecular orbital. So all energies above this will be your, so this would be your LUMO level, this would be your HOMO level, and as more electrons or more molecules take part, these might get the gap might get a little lowered. That is of course going to happen because of the agglomeration. But essentially the LUMO and HOMO formation takes place because of the molecular orbitals interfering with each other. Next, I come to organic semiconductors in general. So that was about the materials, the bonding aspect, and things associated with the materials. I'll now try to discuss a little bit about materials and their properties. Now, if we think in terms of, for example, as I mentioned, one of the important parameters when we talk of semiconductors is the mobility. So there are different class actually that is not visible. Okay, so there are some materials which are being shown. And this is the scale of mobility. So you see organic semiconductors in terms of mobility also they have a very wide range. So they can have 10 to the power minus 5 centimeters per volt, centimeter square per volt second to close to 10 to the power 3 or more than that kind of mobility. So it's a 8 orders of magnitude change in the mobility. So again, which material will give high mobility, which one will be low. All these things need to be further studied to understand how and where you get high mobility and how you get improved mobility of the material itself. Of course, but in general, if you see, they have a very broad range, and typically, so here is the your amorphous silicon, and that is where one important aspect is there. So the commercially available solar cells that we typically see, they are based on amorphous silicon, and then you also have the displays, the TFT based display, which used to be until before the OLED displays have taken over. That is the LCD based display. So LCD based display was using thin film transistors, which were based on amorphous silicon. So what I mean to say is organic semiconductors have over the years, researchers have ensured that the mobilities have improved and have now improved to a level where it can at least surpass amorphous silicon in several of its applications. So in the times to come, we are going to see already one of the most mature technology that has come out of organic electronics is OLED, as you might be aware. So we most of our mobiles that we are using today, and even some of us might be using the displays on our workstation or the tablets that we use. They are basically based on organic light emitting diodes, OLED, and sometimes it is also called active matrix OLED display, AMOLED. So that is based on organic semiconductors, and the simple reason for using LED is compared to LCD. The LED has a better picture quality and a wider viewing angle and all those things. So LCD has a very limited viewing angle, and LCD does not emit colors on its own. Okay, so let us understand that LCD does not emit colors on its own. The typical LCD display that we saw, which was there, I think close to 10 15 years ago, which was typically also used in the computer monitors. Basically, it had a white backlight panel. So this white backlight would be, giving out the white light, and then I will have transistors, and I will have liquid crystal. That's why it's an LCD. So the liquid crystal has a very unique property. Based on the electric field applied, my liquid crystals can be oriented, and they can ensure partial or complete transmittance of the light. So basically, I can control the intensity of light, and I can also, and basically, then we used to put color filters. So blue at each pixel we will have blue, green, and red color pixels, and we modulate the intensity of light, and with that we used to show the I mean the display used to be there. But essentially, LCD does not have light of its own. It has a backlight which is emitting white light, and from that white we are filtering out at each pixel RGB, because to view any picture in its actual contrast, you need to have the information with respect to the RGB content, intensities, and with that you can display any picture. And of course, it all depends on what kind of resolution we are looking at. So that was that era. Now, organic semiconductors, with the organic semiconductors and the OLEDs coming into play, you are typically done away with the requirement of having a filter in place, okay, in the display. So LEDs themselves have their own light. So that's why it is called active matrix based organic light emitting diodes. And here in the bottom, what I have shown is the different types of molecules. So we will see there are small molecules, and then there are conducting polymer based materials, and all of them have over the years their mobilities. This is the best reported mobilities. This is a little older view graph. So you can see their mobilities have improved significantly. All started from 10 to the power minus 5, and now we have gone up to, in some cases, 10 to the power 2, which is pretty reasonable for display, solar cell, and some kind of sensing related applications. And that's where the entire discussion converges. So that is what I was talking about. So this is basically, typically we see this kind of diagram, for when we talk about formation of bands in solids. So the same happens here also. You have different, nuclei with respect to different molecules. And when we say molecular orbital, or basically your band formation taking place in these molecular materials, this is essentially happening due to the overlap of nearby molecules, and as a result of the overlap of the energy levels of the nearby associated molecules. So that is what is being shown here, and this is of course for sodium, just this diagram, but in general this same thing can be extended to all molecular materials. So here is the bottom line. So this is suppose a simple molecule. So a simple molecule will have certain energy levels, discretized energy levels with respect to it. And as we go on, for example, if your molecule has three atoms in it, so these three atoms together constitute a molecule. So this is how the homolumo level would be there. And when this one molecule, so what I'm trying to show is, so this is the isolated molecule, okay, one molecule in itself. And when we try to look into a thin film, it might have several such molecules placed in close vicinity of each other, and that would result in further little bit lowering down of this band gap, that is the homolumo energy level difference. It will be slightly less than that of an isolated molecule. So typically, as we see more of agglomeration, or more of we call this agglomeration, when more number of molecules come in close proximity of each other. So we see that the overall band gap little bit lowers down further, and that is where one of the very important aspects with respect to these materials is there. You can actually come up with techniques and methods by which you can control the extent to which these molecular packing in these materials happens, and with that you can actually control the band gap, and that has a direct impact on whether you are trying to develop LED or you are trying to develop photodetector. So it has a direct impact on that. And then let us also look into the different types of ionization processes. So if light falls onto a molecule, so of course it may ionize the molecule depending on if its energies are as per the required this thing. So it may end up ionizing the molecule. But when we go for you know this is the case of isolated molecule. But when we go for an ensemble of molecules, so what is typically happening in a thin film is there would be several such molecules which will result in the formation of thin film. So in that case, when light interacts with such a system, you will have altogether different behavior coming in, because essentially the band gap, as I said, compared to the isolated molecule would be little lower. So we have shown, for the sake to compare it with the ordered solid, we have shown it like conduction band and valence band, but basically your homo and lumo levels would be actually coming little closer, because the several molecules are taking part and each have their own energy levels. So basically, these energy levels would typically show some kind of what we call Gaussian density of states. Okay, and that would be typically that is typically a characteristic of many of the amorphous solids as well. So in most cases, the thin film that I am talking about is going to be amorphous in nature, or maybe polycrystalline at the max. Of course, it is not going to be crystalline. And before I further go ahead, I'll just also give a brief about, in general, what are the type of materials or semiconductors are there. So we have already seen PPV and some other semiconductors. So in pi conjugated polymers, you have homocyclic semiconductors. PPV is one such example. And in the other class, you have heterocyclic, as I mentioned. It has a sulfur atom in between on the main ring of the molecule. So basically, the lone pair of the sulfur also takes part in the resonating structure, and therefore the delocalization of the electron density on the monomer. And this is the thiophene system. And you have if you have different thiophene molecules bonding with each other, that results in polythiophene. On the other hand of the spectrum, you have, so these are mainly polymers. You see, in pi conjugated polymers, it could be a homocyclic polymer or a heterocyclic polymer. Then on the other end of the spectrum, you have small molecules. So, for example, this is copper phthalocyanine. It's called CuPC is the short form. So it's another molecule which has high mobility, and then you can also have a fused ring compound this is typically your pentacene. So these are basically five rings combined with each other, and this molecule has a special name, pentacene. It's one of the front end molecule because it has high mobility, it demonstrates high mobility. And then you also have oligomers. So oligomers is nothing but if you have limited number of monomers attaching to themselves, that leads to these kind of oligomers. And if you have large number of monomers getting attached, typically larger than 50 or so, you land up with a polymer. So these are different types of semiconducting materials that you come across. And of course, this material over here is typically what is called as the fullerene, and its structure is similar to that of the football. So, and is a very interesting molecule. It is having an N-type behavior, so it behaves as a N-type moiety, and most of the compounds in organic semiconductors, N-type semiconductors are very limited. We have a lot of P-type semiconductors, but N-type is still very limited, and fullerene is one such N-type material. And in fact, the derivatives of fullerene are, commonly used in developing what is called as the organic solar cell. So in organic solar cell, P-type is basically the thiophene, and N-type is the derivative of this material. Um, that is typically used. Now, with respect to thiophene, also, I would like to give a slight, idea about the chemical thing, the structure, how it plays an important role. So, in a corresponds to the alkyl chain that is attached to the monomer unit, and this is the monomer unit. And if you try to see, this is having the alkyl chain or the hexyl chain placed at the third carbon, at the third atom. That's why poly 3 alkyl thiopene. And if you see, there could be two possibilities as these monomers combine. That is, the alkyl chain length either is like head and tail. So this is called a head tail arrangement, or it could be head to head or tail to tail, which is basically resulting out of, if it is a 2-5-2-5 kind of coupling, then it is called head to tail coupling. So for example, this is 2 and this is in this case this is 5. So 2-5-2-5 coupling results in head to head and head to tail, and 5-5 or 2-2 kind of coupling results in tail to tail or head to head. And typically, because of this long chain and the steric hindrance that they cause, if it is a head to head or a tail to tail, that leads to some kind of torsion or twisting of the chain of the polymer, which again has its own implications on the energy levels and things like that. So this basically arrangement of 2-5-2-5 coupling is very much preferred, and the poly 3 axial thiopene that we typically use in devices, mostly we are using the 2-5-2-5 coupling based axial thiopene, which we typically call as regio-regular. So regio-regularity essentially is an attribute that talks about what kind of coupling you have between the different monomer units. And now let me come on to the optical excitations. So if you look at the optical excitations in these materials, so typically if you, this is your ground state and these are your excited states. So you can end up, if you excite these molecules with energy that is higher than their band gap, you typically may excite, from any of these energy levels, that is, sorry, your ground state energy level to any of these excited state vibrational levels. And typically, the absorption of light results in different transitions, which we actually look at. In fact, on an energy scale, if we place all of these transitions, so there is a 0-0 transition which overlaps with the 0-0 of fluorescence and absorption overlaps. So as these kind of materials, when they absorb light, that typically results in what is called as the absorption spectrum. And when they emit light, because what happens is, suppose if an electron has been excited from 0-0 to, let's say, 5-1-2, that is the second vibrational state in the excited state S1. So what happens is, since it is in a relatively higher energy state, it will tend to, through by means of molecular vibrations, it will tend to lose some of this energy and come to the 510 state of S1, and from there it may return back to the ground state, and that leads to what is called as the emission. So typically, all other transitions, there is a one-to-one correspondence, 0-1, 1-0, 0-2, 2-0. So there is a one-to-one correspondence with respect to the energies. So this can be thought of with respect to energy in the coordinates as some kind of oscillating pendulum kind of structure. So maybe as we try to excite, so this is in the higher energy state, and these are the vibrational energy states that we are referring to. This is just an analogy to make you understand what exactly we are talking about. So basically, one important point to be noted over here is, as you can see, the energy level or the energy state of absorption energy levels are much higher than that of fluorescence energy levels. That means typically the emission of light would be having a red shift in the wavelength compared to the absorption. And before we go ahead, I'd just like to mention how light, interacts with materials, these kind of materials. So typically, we look into the absorption and emission of light to understand the optoelectronic behavior of the materials. And if you have a beam of light incident on your material, typically there are various possibilities that may happen. You can have reflection of light, transmission, absorption, as well as scattering. So these are all possibilities that exist when light interacts with matter. So what I'm referring over here is basically if you have an incident light, certain part of it might get absorbed as it passes through a material medium, and you may end up transmitting a light, a certain amount of light, and that is by studying the difference in the intensity of the transmitted light and the incident light, we can find out at what wavelength how much of the light was absorbed by the material, and from that you can estimate or see the what is called as the absorption spectra of the material. And these absorption and emission spectra are something like thumbprint of the materials, and give us a lot of information about the material properties in general. So, in a typical molecular, in a typical materials like organic semiconductors, the absorption happens, if my incident light has an energy which is larger than the band gap, that is the difference between the LUMO level energy and the HOMO level energy. So, if it is having energy larger than that, that will typically result in some kind of electronic transition, and which basically leads to absorption of light in these materials. And if light does not get absorbed by a molecule, then it would be typically scattered by the molecule. Okay, that is what we call as the some kind of the scattering of light that we see typically in the case of the colloidal solutions. Okay, so if you have some kind of colloidal solutions, you will have scattering of light taking place, and in case the light is absorbed by the material itself, you will have so basically by studying the transmitted light through a material, so I can have a clear-cut idea at what all wavelengths does my material absorb the light. And the basic law that it follows is called as the Beer-Lambert law. And the Beer-Lambert law is essentially talks about the light, if it is incident on a material having a cross-sectional area A and the thickness, certain dx thickness, and the concentration of the species which is absorbing is C. So basically minus di by I, that is the change in the intensity over the intensity of the light that was incident, is proportional to the product of sigma C and A and dx. And finally, if we try to simplify, this comes out to be, so I'll come on to the final part of it. So if saturation effects are not there, then this is what it relates. So if you have some intensity of light incident onto a material, this is the light incident onto a material, that multiplied with the exponential minus alpha x, where alpha is the absorption coefficient of the material and x is the thickness through which the light is traveling inside the material. This is how the intensity of transmitted light will relate to the intensity of absorbed light, incident light. So basically, from this we can find out. So looking at, if you look at this expression, ln I by I naught will give you minus alpha x, and straight away from that you can actually measure your or find out your absorption coefficient of the material, and in fact you can study the absorption spectra of the material as well. So this is the transmittance, it is I lambda by I naught lambda, and you take a logarithmic of this, and typically absorbance, they add up. If you have different absorbers, so they typically add up to give you the total absorbance in a system. And this is the UV vis spectrophotometer. So the whole idea is you have a light source which is giving polychromatic light. It is being passed through a monochromator, and you get certain fixed intensity light out of this monochromator, which is made incident onto the sample. And this intensity of light which is getting transmitted and the one which is made incident, the difference in these intensities is being then looked at by the detector to get a graph like this, which is corresponding to the absorption of the light at particular wavelengths in the material. So that is a material property, and that is what is typically termed as the absorption spectra. And as I said in the Beer-Lambert law, so absorbance is directly related to epsilon, and this is the path length of the light inside the material. This is the absorption coefficient, and this is the concentration of the absorbing species. So typically absorbance versus concentration plot, if you see, it comes out to be linear, and the slope of this, so absorbance versus concentration should be linear, and slope of this would be epsilon times L, and from there you can calculate the absorption coefficient. Okay, and then comes the emission spectroscopy. So fluorescence spectroscopy, on the other hand, is having basically spectra. You can look into the spectra of emission spectra of these materials. Again, why emission spectra is important? Because once I know the emission spectra of a given organic semiconducting material, I can have a clear-cut idea how much this material would be useful if I want to develop or use it for applications such as LEDs or solar cells. So studying emission spectra straight away gives me a direct or is a first-hand direct indicator of suitability of a material for optoelectronic applications. So that is why studying fluorescence spectroscopy is important. And of course, these are a lot of details, but I'll just mention. So you have some kind of excitation. Maybe I'll just go on to the next slide. There are basically excitation source and then non-radiative and radiative transitions or recombinations, as we call it. So that is happening inside the material. So maybe it all will make sense over here. Okay, yeah. So this blue lines indicate the excitation by the external light source of the material, and then the electron might be excited to higher vibrational energy levels, and then it may relax to the ground state, and then it can finally recombine, because one important thing that we must bear in mind, that charge carriers cannot stay in high energy state for an indefinitely long time. So if we have excited the material, it also in fact happens at a very short time scale. At least finally the excited carrier may come back to the ground state. So if it follows this path and recombines, because you have a once it was excited, you have an electron here and a hole here, and finally that electron relaxes from the higher vibrational energy levels to the ground state of the excited state, and from there it returns back to the ground state of the molecule. So if you have this kind of scenario, then basically you have the fluorescence taking place. So this is okay. The green one over here is non-radiative transitions, and this is the fluorescence. So if you have a direct transition from the ground state of the excited energy to the ground state, basically. So basically, this is S1 naught and this is S naught naught. Okay, so if you have a transition like this, that is what results in fluorescence or the emission of light. So fluorescence is essentially emission of light, and one of the very simple and the most common example of fluorescence happening in nature is your fireflies. Okay, that is the example of bioluminescence. And besides that, a lot of other applications are there with respect to luminescence. So again, I'll not go into too much of details of it. But what I would like to mention is studying the fluorescence spectroscopy also gives us a good amount of idea about the vibrational energy levels of the molecules in general. And as I said, fluorescence spectra directly relates to the electroluminescence as well as the or basically the LED or the solar cell related behavior of the molecule. And typically absorption spectra, so this graph shows an absorption spectra and an emission spectra. As I said, that they will be a little bit of sort of mirror image of each other in some sense, and most of the peak positions are mirror image, and typically emission spectra would be red shifted. So this is on the wavelength scale. So if you draw a graph of these kind of spectra on the wavelength scale, you can convert. So these graphs can be seen on wavelength as well as energy scale. So if you want to see them on energy scale, you just simply calculate, convert the wavelengths into energy. So whatever you are seeing, the higher the wavelengths, lower is the energy, right? So if you see the emission spectra are a little bit red shifted. We call this red shift because it is going towards the red side of the wavelength of, in that sense. Okay, so red shifted compared to the absorption spectra, and the reason being because in the excited state the electron tends to relax to the zeroth vibrational level of the excited state before it recombines. And then this is, if it is recombining, it is emitting light. It might also happen that the electron does not recombine, and that is what we call as quenching. So there are different reasons for quenching, and it can also undergo non-radiative transition. So non-radiative transition does not lead to any light emission, and that is sort of a loss of energy to the system. So typically all these possibilities exist, and in fact when we study a fluorescence spectroscopy, we look at what is the extent, how much of the excitons actually are undergoing fluorescence compared to the non-radiative recombinations or transitions, and which again is basically termed as the PN efficiency. So this is just to give you an idea about the different spectrum, the electromagnetic spectrum of light, and typically we have from the 400 to the 400, that is blue region, to the 700 nanometer, where we have the visible wavelength band, and below 400 you have the ultraviolet region, and above 700 you have the infrared or the IR region. So I have already talked about this, so I'll just skip this. Basically, this is about the excitation of light and the emission spectra. And I'll come on to the different types of luminescence that we come across. So if you have a spontaneous emission from solids taking place, that is basically what is called as luminescence, and especially if you have semiconducting materials, the emitted radiation carries material signature and can be used as a diagnostic technique, and is a powerful tool for low dimensional semiconductors. Besides this, if you look at the fluorescence, it's the fast luminescence. Typically, the time scales that we are looking at is that of nanoseconds. And then there is a delayed fluorescence, which we call phosphorescence. I'll come on to that. What is phosphorescence? Essentially, what is the difference between fluorescence and phosphorescence? So phosphorescence typically happens at a time scale of micro to millisecond time scale. So it is much slower recombination. This is also radiative recombination. This is also radiative. But typically the slower radiative recombination is termed as phosphorescence. And electroluminescence and fluorescence are one and the same thing as far as the emission of light is concerned. It is one and the same thing, but the only difference is, and why we have the two different names, is basically in the case of fluorescence, the excitation of the material was also caused by light, and was caused by light. But in the case of electroluminescence, the excitation of the material is caused by electrical excitations. So that is the only difference, but both will give you emission spectra, which will be of this time scale. Okay, and then in some semiconductors that we come across, it might be in the picosecond time scale also. And then the cathodoluminescence is basically based on some kind of cathode ray based excitation. And anyway, we are not going to look into timing of our discussion, or the purview of our discussion. Then I'll talk about this photoluminescence spectroscopy, why it is so important, and basically it can be used to measure the purity and the crystalline quality of the semiconductors. You can also use time resolved PL to determine that what is very important is the minority carrier lifetime of semiconductors, for example, gallium arsenide or any other kind of semiconductor. So many different semiconductors actually give fluorescence spectra, and typically one of the important requirement for a material to give emission spectra is that it should be a direct bandgap material. So if you have a direct bandgap material, and most of the organic semiconductors that we are discussing, they fall under the category of direct bandgap materials. Silicon, like for example, is an indirect bandgap. So in silicon, you will typically not see fluorescence related discussions happening. And uh, basically these can be used to determine the structure, concentration of the emitting species, and all of those things. Uh, Again, if I look into the experimental setup of a photoluminescence spectroscopy, so what we do is we use a laser which excites. So this laser is of course shown onto a mirror and then being diverted to a sample. My sample is here inside the cryostat, and once the laser strikes the sample, it excites. If the energy of the laser is larger than the band gap of the material that we are trying to characterize, it will excite the material, and that will lead to formation of electron holes. And when these recombine, that gives rise to emission of light, and that emission is being captured by means of these lenses onto the spectrometer, and then it is being recorded, and that's how you end up recording your emission spectra. And we have PL spectroscopy, which basically and then of course the time resolved. So time resolved and continuous wave based PL, the only difference is here you can actually look into the the uh, the what is called as the radiative and the non-radiative lifetimes. You can actually determine those, and once you have radiative and non-radiative lifetime known to you, you can calculate the radiative and non-radiative recombination rates, and based on that, you can calculate the overall efficiency, emission efficiency of the material. So, in general, okay. In general, whatever is the total number of after excitation, whatever number of total number of excitons that are created. So, okay, I'll maybe go to the next slide first. Maybe yeah, this slide, and then I'll go back to that slide. So, what is happening is when we excite these materials, typically, the electron transition results in electron and hole formation. And one of the interesting thing about these materials is that the dielectric constant of the material and the band gap is such that these electron and holes tend to still extend some kind of coulombic, attractive force onto each other, and that results in formation of what is called as the excitons. And these excitons actually there is certain binding energy associated with them. So if we are able to provide some additional energy larger than the binding energy of these excitons, then only they tend to undergo dissociation into charge carriers, or otherwise they will either end up undergoing radiative recombination, which will lead to light emission, or some kind of non-radiative recombinations by certain mid-gap states or intermediate states, or by means of phononic vibrations. So these are the typical scenario. So I will try to put it all in a single. I'll try to put it all in a single slide. So basically, the excitons that are getting formed. So we excite the material with light, and that leads to formation of excitons. These excitons can be dissociated into charge carriers by means of electric field. This is what typically happens in the case of solar cells, and these can undergo radiative recombination. So, exciton formation, exciton undergoing radiative recombination is what happens in the case of LED. Okay, so essentially, if you understand the energy band diagram properly, you will be able to comprehend a lot of things about the devices in general by excitons are formed only when excitation you provide excitation, whether it is in the form of electrical or optical. In many of the semiconductors, especially the direct band gap semiconductors, mostly you will find that the excitons are pretty stable. Okay, and then it all depends on their binding energy. For example, if I talk about zinc oxide, so zinc oxide at room temperature has exciton binding energy of 60 millielectron volt. So 60 millielectron volt would mean that the energy binding energy is larger than, because what is the thermal energy for semiconductor devices? It is 25 millielectron volt. You might have studied, right? So the thermal energy is 25 millielectron volt. So if I say that my energy of binding energy of excitons is 60 millielectron volts, that means the thermal vibrations are not going to cause any disruption to my excitons. They are formed, and if their energy is larger than the 25 millielectron volt, typically the thermal energy is by virtue of the temperature. Okay, the room temperature itself leads to certain amount of agitation in the electrons, which we call as the thermal energy, which we typically quantify as kTm on cube. Okay, and the value comes up to be, which is Vt, which is coming out to be 25 millielectron volt, or exactly is 26.8 millielectron volt. So basically, if my energy is larger than that, 60 millielectron volt, that means this thermal energy is not enough to dissociate the excitons. So excitons are pretty stable. Okay, and in such a system, you will get good luminescence. So that's why in zinc oxide you will get a very nice luminescence. Okay, if you excite zinc oxide with a blue laser or near UV laser, you will get a very nice emission, which is the characteristic of zinc oxide. Similarly, in these materials also you will see a good amount of emission. And if, however, on the contrary, my binding energy is less than 25 millielectron volt, in that case, this room temperature vibrational energy in the material is itself so large that it ends up disrupting the excitons. So excitons would be stable if the exciton binding energy is higher than Vt. And what I'm trying to suggest over here is, if you have external electric field, okay, so these are the some other energy levels, like if you consider a solar cell. So if you you end up forming excitons in the solar cell once the light is illuminated onto the thin film, and these excitons, they end up dissociating into respective charge carriers if there is a built-in field. Now, this built-in field in solar cells is created by virtue of the work functions of the metals that are used. Okay, there is a low work function metal which is cathode on one end, and there is a high work function metal which is the anode on the other end, and their work function difference itself creates a certain amount of gradient, potential gradient, which leads to a built-in field in the device, which is responsible for this kind of dissociation into charge carriers. Okay, so what I'm trying to suggest is this emission spectra using PL, it gives you direct indication. So, for example, if for a material, if I'm shining it with light, there is a high luminescence that is happening, and if I'm trying to, do some processing, and this material, this radiative recombination or the PL signal is quenching, then and if I'm also able to simultaneously monitor that whether it is leading to some kind of photocurrent. So yes, if that is happening, then that in that case This material is highly useful for solar cell related applications. So the only difference between normal fluorescence and electroluminescence is, in the case of electroluminescence, you end up creating these excitons by means of electric charge injection from the two electrodes. Okay, that is what happens in the case of LEDs. So in the case of LEDs, the process is just reverse. You end up injecting charge carrier into the LUMO and into the HOMO from both these respective electrodes, and these injected charge carriers then tend to recombine. That is what leads to emission of light. So the process is just reverse in that of LED and the solar cell or the photodetector. Now I'll come back to the previous slide. Yeah, so basically what I'm trying to suggest over here is the total excitons formed will undergo either radiative or non-radiative recombinations. Non-radiative would lead to loss in the system. Basically, non-radiative would be then equal to probably there would be some which is taking part into photocurrent generation, and some would be sorry, this is phononic vibration pH, and some that would be getting dissociated into charge carriers. So if you look at it, the total excitons is sum total of excitons undergoing radiative recombination, and the non-radiative part further is sum of NPH and N dissociated. And if you look at the efficiency of the PL system, PL process, basically that would be ratio of Kr to that of Kr plus KNR, and KNR here is again segregated into KNR plus KQ, which is to denote the field assisted dissociation. So what it boils down to, if I get emission spectra of a material, for example, over here one graph is shown. So this is basically P3HT's emission spectra, and what we have done is we have coated some 20 nanometer aluminum over it. So this black one is 97 nanometer film, thick film of P3HT, and then we coated it with the 20 nanometer aluminum. So as you can see, the emission counts dropped from this. If you can see these shoulder peaks, this one and the main peak, these are all, the features are all retained, but the intensity gets decreased. So you see from the black to the red curve, just by coating aluminum. So what is happening here is aluminum is leading to, because the aluminum forms some kind of Schottky junction at the interface, and which leads to strong decay of excitons at the interface, and therefore a lot of excitons undergo non-radiative recombination. So increase in non-radiative recombination may lead to decrease in the overall PL counts. As you can see, these are the PL counts. So that results in what we call as PL quenching. Okay, so basically the efficiency of the entire PL process would be directly proportional to the radiative recombination rate divided by radiative plus non-radiative plus field assisted. So in case if in some material your KQ is high, then that is a very good material for solar cell related applications. And in case if your this KNR and KQ are very low, then the material is highly suitable for LED applications. So studying fluorescence spectroscopy gives us a direct indication about the suitability of material. So like I said, exciton is the basic entity that we are studying when we are looking at the emission spectra. So exciton is the basic entity that we are trying to study, and these excitons can be photogenerated if we are shining light onto the thin film, and these excitons can be on the other hand electrically generated. And in case of electrically generated, there is some kind of spin statistics that needs to be followed. So typically 25% of them will be singlet and 75% would be triplet states. So singlet corresponds to when we have the electron and holes have opposite spins, and when we have the same spin, then it is a triplet state. And in the beginning I told about phosphorescence. So phosphorescence is essentially fluorescence coming out of triplet states, and typically the fluorescence out of triplet states is usually on a delayed time scale, as I mentioned in the initial slide, that is on a millisecond to microsecond time scale, and that leads to slower fluorescence. And if you have electrically generated excitons, then the luminescence that you study is electroluminescence. If you have photo generated your excitons by shining light, it will be 100% singlet. There will be no triplet states in that case, and that would be basically your photoluminescence. So that is the entire idea about luminescence. So studying PL is basically studying about the overall exciton dynamics in a material. So this part I already explained. And now let us come to the final conclusion of it. So if you study a photoluminescence spectra, the characteristic PL frequencies and the peaks at which these PL peaks appear, it tells you a lot about the composition of the material, and changes in the width of these peaks talks about, or you can estimate the quality of your material, that is how much crystalline the material is, and if there is any change in the frequency, either it shifts on this side or that side, then that can be attributed to some kind of stress or strain on the films. So that may result in shifting of these frequencies slightly, and the intensity of the PLP is directly correlated to the amount of excitons or the emitting species. And of course, you can also have polarized light made to excite your thin films. And in that case, what we end up is what that is called polarized PL, and that can be used to study the symmetry or extent of orientation. So today in my talk, I'll be finally coming on to some of these points. And in terms of excitons also, just to your knowledge, there are mainly two types of excitons in semiconductors: the Frankel excitons and the one-year Mott excitons. One-year Mott excitons are typically formed when electron is bound only very weakly with an average radius larger than the lattice spacing. So typically, in such circumstances, you end up with WM excitons, or the one-year Mott excitons. And the exciton dynamics in these materials is usually described by the effective mass and the type of excitons and the binding energy. Binding energy is typically of the order of 10 milli-electron volt, and Bohr radius is of the order of 100 angstroms also. And permittivity constant is usually larger in these materials. So that is what my this one-year Mott excitons. And on the other hand, the Frankel excitons would have typically the electrons are bound strongly, and they are essentially confined to a single lattice constant. Okay, so instead of extending over certain several lattice constants, it is up to confined up to a single lattice constant. The exciton propagates through energy transfer process only in these materials. It does not directly transfers its energy otherwise, like in the case of WM excitons. And typically their energies are of the order of zero point 0.1 to 1 electron volt, which is relatively much higher. And the Bohr atomic radius is close to 10 angstrom, and the permittivity constant is usually smaller in this case. So that is about the two types of excitons, and so this is the complete picture. So if you have strong covalent bonds, you have weak disorder, and that will lead to good charge transport. But the excitons would be in that case loosely bound, and that may result in some kind of non-linearity in these materials, and there would be of course weak interaction with phonons as well when we talk about the overall charge transport in these kind of systems. So here are some of the examples, like your zinc oxide, zinc telluride, zinc selenide, Cu2O. These are all inorganic semiconductors where you will see one-year Mott kind of excitons typically are formed in these systems. And on the other hand, in case of Frankel excitons, you have weak van der Waals bonds, and that lead to strong disorder. And the charge transport is relatively poor. It's not bad, but it's poor actually. And the interaction with phonons is rather more pronounced. Okay, And in this case, what happens is the excitons are rather tightly bound, so the oscillator strength is large. So that is the difference, and most of the organic semiconductors you'll see fall under the category of. So the Frankel excitons are typically formed in organic semiconductors. Examples are anthracene, pentacene, porphyrin, and a lot of materials that we discussed today. Can we take a short break? Yes. So we can have a short break. 10 minutes. 10 minutes. Oh. 10 minutes tea break. Okay. So, so we discussed all this. And now we come towards what is called as the energy transfer. So once you have, these excited molecules, so sometimes, they tend to transfer their energies, and that process of transfer is what we call as FRET, fluorescence resonance energy transfer. And the idea behind FRET is, suppose you have some donor kind of molecule whose absorption and emission spectra are like this. And then there is an acceptor type molecule whose absorption and emission spectra are like this. So what happens is, if these two moieties, that is donor molecule and acceptor molecule, are in close proximity of each other, so what will happen when I excite this donor molecule? Of course, it will absorb wavelengths, light in these region of wavelengths, and this excitation would finally lead into absorption, emission in these region of wavelengths. And since there is a large overlap of emission of molecule 1, that is donor molecule, with the absorption of molecule 2, there is a large overlap, as you can see here. So what happens is, I have excited this molecule, but it ends up transferring the excitation, and basically your excitation or excitons are nothing but energy. They are having the energy that was provided by the external photons. So that energy gets transferred to the acceptor type molecules and finally results in fluorescence. So this phenomena, if you have energy transfer taken by these means, is what is called as fluorescence resonance energy transfer, or FRET in short. And typically it happens at a length scale of around 10 to 100 angstroms. And you have one of the conditions for FRET to happen is that the donor and acceptor fluorescence and absorbance spectra must overlap significantly for FRET to happen, and the donors transfer non-radiatively, they transfer their energy to the acceptor molecules. And as is also evident, so since one of the molecule is transferring the energy to the other molecule, this all this will be very critical to the distance between these molecules. Okay, so in fact, FRET has been utilized to develop some kind of FRET-based sensors. It has been utilized to study some very elementary and simple biological processes or biochemical processes. So there is a lot of things that can be done using FRET, and this is just one example. So you have a donor type and an acceptor type moiety, and if this condition is satisfied, then you end up having FRET transfer. So this is how it all happens. So we excite one of these molecules, and then as it emits, it re-excites the other acceptor molecule, which probably usually have a little lower band gap than the original molecule. And the typical energy transfer efficiency in this case is basically KET, corresponds to the energy transfer rate constant, and the sum of all the other type of constants. So it is KET divided by KET plus summation KI, where these are not energy transfer uh, uh, constants. So that is the overall the transfer efficiency. And what I would like to emphasize again over here is that in this kind of energy transfer also there are two different types taking place. One is Foster energy transfer, where you have resonant dipole-dipole kind of coupling happening between donor and acceptor molecule. Typically, this happens at a length scale of less than 100 angstroms, and usually it is a very fast process, as you can see, happening at a time scale of nanoseconds. And what is happening here is you have excited the donor moiety, and the donor has now electron and hole, or the exciton in it, that was created as an outcome of the excitation. Now this exciton then ends up transferring its, so basically this is sort of the emission of this is captured by the absorption of acceptor, and finally you end up having this kind of electronic configuration. So this is basically a singlet transition typically, and this is what is called as the Foster transfer. And there is another kind of transfer that can happen. So this is little more details about Foster transfer. Anyway, I will not go into that much detail. So basically, this type of Foster transfer typically bears some kind of this relationship to the power of 6 on the distance between the molecules. So using that, we can actually find out whether it's a Foster type or a Dexter type. So the other energy transfer that is mechanism that is possible is Dexter type. So in a Dexter type, what happens is so you have this electron hole of the donor, which is having higher band gap, and that is in the excited state. But what happens is it's the electron which gets transferred from the donor. In the previous case, it was not electron; it was just the energy that was getting transferred. So in a way, of course, this is also a means of the energy getting transferred. So you excited donor molecule, the energy was captured by donor molecule, but finally it ends up getting transferred to the acceptor molecule. So, but in this case, there is a electron transfer also happening from donor to acceptor, and and that from acceptor to donor, and that's why this kind of you know transfer is termed as Dexter energy transfer. So there are two types of energy transfers, and typically you have only singlet or triplet kind of transfers being allowed in this case, and the length scales at which Dexter transfer is more prominently seen is at a length scale of 10 angstroms. Typically, these are used in some case of dye molecules. So again, that is a little bit of too much details of chemistry. So where dyes are used and what is the purpose. But if you are aware, in modern day third generation solar cells, thin film solar cells, of course, the thin film solar cell, organic thin film solar cells are one candidate. There is another candidate which is perovskite solar cells. Perovskites are some kind of organic inorganic hybrid kind of materials. And then there is another candidate, dye-sensitized solar cell. So in dye-sensitized solar cells, these concepts play a major role. So anyway, and then you can also have non-radiative energy transfer also taking place in these material systems. So, for example, if you have a so basically to sum it all up, so if you have a Coulombic kind of attraction and the Foster-based energy transfer, the length scales are typically long, and you end up having singlet transfer. Whereas in the Dexter kind of this thing, electron exchange also takes place along with the energy transfer, and the length scales are relatively shorter, and you have singlet or triplet transfer taking place in this case. And with that, we finish the second part of the today's talk, in which I have tried to explain some of the underlying concepts by means of which we can understand the properties of these materials. Now, I will just quickly rush through some of the broad classification, and also coating techniques. So, so organic semiconductors, as I mentioned in the very beginning, the one of the major advantage with these class of materials is they are solution processable. Not all of them are solution processable. So then, which are solution processable? So one of the simplest thing I would like to mention. So if you have seen, I talked about poly 3 hexyl tyrosine on which there was a hexyl chain. So presence of a long alkyl chain makes the organic compound soluble in commonly known solvents like chloroform and other dichlorobenzene and several other solvents. And then of course you need to little bit delve into the chemistry. But let me tell you again, as I said, this is a highly interdisciplinary field. So inputs from various different domains are required. As a device physicist or as an engineer, we would end up using these materials. There is another group of chemists or people who can actually design these materials because not all these tasks it is very almost impossible for a single person to do, right? So it involves a lot of interdisciplinary efforts to do these things. Now, as I said, if you have presence of long alkyl chain on the molecule by means of certain substitutions at certain site, you can make those molecules solution processable. For example, these are some of the polymers that are solution processable: P3HT, MDMO, PPV, PFO, and several other MEHPPV. So these are all polymers which are typically soluble, and these the large or the macromolecules that are the polymers are typically solution processable. On the other hand, you have another class of organic materials which are actually not solution processable and usually are vacuum sublime. So vacuum sublime means I am not sure how many of you have actually any exposure, but I'll just maybe we'll talk about it in subsequent slides. So probably you will understand. So what we do is we in a chamber we first lower down its pressure. We take it to low pressure condition, and then we create vacuum, and then we sublime or heat these materials. So pentacene, anthracene, all these are small molecules, and when heated up to their melting point, they would typically transfer at that pressure and temperature conditions. They typically get transferred from the solid state directly to the sublime state, and they end up getting deposited on the substrate. So we'll see that. So that results in thin film formation. So this is another way of fabricating thin films. Now I'll just talk about various solution process techniques that are possible. So, for example, if I can make these materials soluble in a solvent, I can make inks of these materials. And once I have inks of these materials, I can play a lot with respect to techniques like spin coating is very common. In fact, spin coating was a technique which came much before organic semiconductors came, because spin coating was actually done of, if you are aware, if any one of you have worked in fab lab, so typically for carrying out the photolithography also spin coat the photoresist materials, negative or positive photoresist materials. So the spin coating technique has been there much before the advent of the organic electronics. However, after organic electronics came into picture and we had a lot of these molecules which can be actually dissolved in solvents, this technique has even taken much more prominence, because basically that would mean that you can simply spin coat. So in spin coat, you usually use a chuck. I will show you what is spin coating. And then there is a drop casting or casting technique. You can have a dip coating technique, drawing, electrochemical deposition, printing. Printing is very important, as I said, because in fact one of the biggest prospect of making the entire sensor development solar cell, or all these things that we are talking about, is that if it all can be printed. So if you can come up with this technique, printing technique, and if you can ensure good thin film formation by formulating inks of these materials properly. So basically, we are able to, just like your ink is being printed on paper, similarly we will be able to print devices on paper or some other flexible substrates which can be used then for demonstrating some kind of flexible electronic systems. Then doctor blading, LB film, this is a very specialized technique, LB laminate logic film, and then you have spray coating. So these are all different, and the list is not yet over. I mean, there are some other additional techniques. This is not an exhaustive list, but still to list some of the commonly known, techniques that are there for solution processing. Now I'll talk about spin coating. So spin coating is typically, you have a vacuum chuck and there is a very fine bore here through which it is connected to a pump, and you place your substrate, and when the vacuum pump is switched on, this because of the suction, the substrate is held to the chuck, okay, and on the substrate you drop your solution, and then you set some you preset some time and some rotation speeds, typically 1000 rpm, 2000 rpm or so, and certain time, 30 second, 40 second, like that. And when you suddenly accelerate or rotate it because of the centrifugal forces, what happens is suddenly this entire material, you know, fills out the entire substrate surface, and because of rapid, rotation, the and usually the solvent used is volatile, like for example chloroform. Chloroform is a very volatile solvent. So what happens is it evaporates, and the solid that is left out is your thin film of the molecule, or molecular thin film of the material that you wanted to coat. So you end up getting this kind of thin film by rotating the substrate at typical speeds of 1000 or 2000 rpm. So of course, the technique comes with its own some kind of issues also. So it is used for preparation of ultra thin films of high degree of smoothness. It is widely used and adapted technique, and totally reproducible. Thick film coatings is also possible, although generally it results in larger surface roughness. So the rule of thumb says if you can dissolve a substance, it is possible to cast a thin film of that substance using spin coating technique. And these are the parameters that matter. So the concentration of the solution, the molar mass, the choice of solvent, choice of substrate, and spinning speed. All these determine what kind of speed or what kind of thin film you may end up getting. Usually, concentration is the main factor, although these are all the factors that influence, but the greater is the concentration of the solution, thicker films, and it directly relates, and of course, the rotational speed. So, if I am rotating substrate at a higher speed, I'll end up with a thinner film, okay, formation. But if you typically see, because of this rapid mechanical rotation, what happens is I have dispensed large amount of solution, most of it gets spilled over. Okay, so there is a lot of material wastage here. So again, with each technique comes its pros and cons. So there is a lot of material wastage here. On the contrary, there are some other techniques like dip coating. Dip coating simply is you take the solution in some container or something, and you dip your substrate into the solution and then retract. When you retract it, the thin film of this material gets coated onto the surface. And in fact, in industry, many things are the coating of a layer or a paint is done like this in industrial processes. So it is very similar to that. And in the kind of dip coating that I am referring to, fraction of millimeter per second to 1/100th of millimeter per second is typically the desired speed to have a a good kind of film getting coated. So anyway, drop casting is another method. Here we simply dispense the material and let it evaporate naturally. It can be left to evaporate in air, or you can put some kind of beaker to make it a more confined and more slow process. The slower it evaporates, the better film and more aggregated film you will get. So, but of course, the limitations here are that this will result in typically very thick film. Material wastage is not there, but this would result in much thicker films than what you can get with spin coating and tip coating. But of course, and thickness would be hard to control in this case. And in some cases, uniformity would not be there across the substrate. Somewhere it will be more thick, and somewhere it will be less thick. So there would be a lot of non-uniformity. So that those are some disadvantages. But in terms of aggregation, because okay, so again I would like to put it, the rule of thumb is, if I am trying to, because you see all these approaches, especially when we have the solution and we try to put a thin film, basically what we are trying to do is, we have the material in liquid state, and when we are trying to build it bring it into solid state. Okay, so all those techniques where you give large time for solvent evaporation, and you allow large time, so molecules can come closer and form well aggregated structures. So all those techniques would result in much more aggregated structure and probably larger crystallinity. So in terms of aggregated structures, this would have much more well aggregated structures compared to spin coated. Spin coated would lead to more of a random kind of arrangement of the molecules inside the thin film. But here it would be more well packed structures, and but on the contrary, here the thickness would be much larger. So that is the disadvantage. Then there is this bar coating. Bar coating is simply, you can have some kind of textures on these bars. This could be there is some special metallic bars that are coming. So using this, so it is basically very similar to if you have seen commercial screen printing kind of things which used to be there. Of course, now the times have changed. Everything you get it done through computers. But again, 15, 20 years back, if we go for getting a pamphlet or something printed on a piece of paper, we would typically take it to the printing guy, and they would have machine which is called screen printing. So using screen printing and the template that they used to print it over the entire substrate. So this is very similar to that. So you have this kind of bar, and you first drop your solution and then you spread it out using this bar. It is not very good to do it manually. You can probably make it much more precisely controlled by means of some kind of interfacing. But basically, this also results in some unidirectional, alignment of polymer chains, as you can see here. So the parallel oriented and perpendicular oriented have different levels of mobilities compared to spin coating. So this can lead to a certain degree of anisotropy in the material. So this is the bar. It has a spiral pattern on itself, and when this bar is moved over the solution, of course it spreads out the solution, and leads to coating of the layer on the substrate material, and of course is used for device fabrication. Then you also have screen printing, as I mentioned, screen printing using shadow mask technique. So you can, so the solution of active material is squeezed by a moving blade. And again, if you do it more of a manually, then you can call it doctor blading. And if you do it in a more precise way using proper microcontrolled machinery, so then in that case it would be sort of a screen printing. And of course, the resolution in typically screen printed case would be that of 50 to 100 micrometers, which is quite large. So of course, these are not suitable for lower resolution devices. Then you have the the shadow mask. So this is called a shadow mask. So if I make these masks, I can make using metals. So what is being done over here is, so for example, this was the substrate, silicon wafer substrate, and on this you have an oxide layer on top, SiO2 layer, and below is silicon wafer, and then we do a treatment with what is called as the silane. So octodecyl trichlorosilane, ODTS, and then that leads to self-assembled monolayer, which makes the surface highly hydrophobic. And then we deposit metal. While depositing metal, because these metal electrodes are going to be sort of source drain electrodes for my the organic field effect transistor. So I use this kind of shadow masking technique to pattern these electrodes, and then finally use these. If I illuminate by UV light, so what happens is these source drain electrodes actually prevent the damage of the ODTS by the UV light below it, but otherwise it is damaged everywhere. So there is of course some reason for the purpose of it. So you can refer to this paper. So basically, the change in the hydrophobicity is characterized by the this is a water droplet on the substrate. So you see a hydrophobic substrate. Hydrophobic means water droplet will take more of this kind of shape, okay, because water does not have an affinity to stick to this surface. So if your contact angle is usually greater than close to 90 or even greater than 90, then that those surfaces are called hydrophobic. And if your contact angle is something like below 30 degree or so, it is typically basically a hydrophilic substrate. So for most of the organic materials, organic semiconductors that we are going to coat, we would prefer the surface to be hydrophobic and not hydrophilic. So using contact angle measurements, we can ensure that and see whether my surface or the surface energy of the surface is matched with that of organic semiconductor or not. And in case if it is not, I can do UV ozone treatment or UV ozone exposure. Then basically there are some other ways by which you can do some kind of coating of materials. So one is photo patterning. So in this case we take a cross-linkable material, and when once it is exposed by means of mask, certain regions are exposed to UV, and that leads to cross-linking, and then the regions which are cross-linked, then we, using an etching solution, we etch the remaining part, and the crosslink part remains on the surface. And these kind of structures can be developed, and they have been used for patterning of pixels in OLED display. You can refer to this report to see what exactly was the work, or get more details about the work. And then, of course, one interesting part is the soft lithography. So, the soft lithography is little different from conventional lithography. So, basically, if you see the lithography process, it talks about making the feature size more and more smaller. I mean, more and more smaller because in silicon we have started or progressed like that. So we have always been trying to miniaturize our devices. So, but basically, photolithography talks about patterning of the substrate. Okay, now, in this case, with these soft materials, actually patterning, like in the case of silicon, is not possible because, and in fact, one of the beauty why till date, there are materials. Again, I would like to emphasize there are materials, which have even higher mobilities at room temperature than silicon. Okay, for example, in today's time, you can very easily demonstrate a carbon nanotube based transistor, and you can demonstrate that my one transistor is functioning better than silicon transistor. Okay, it is possible. It is possible, but there are materials which have much higher mobility even than silicon. But still, if you see mainstream, all electronics that you see, especially in the mainstream, what we are looking at is microprocessors, memories, your from the pen drive to your SSD drive of your computer, everything. It has been silicon based, and till date, despite so many material research, none of the materials have been able to substitute silicon. Can anyone tell me why? Why is it that silicon, despite having um, lower mobilities, so
In terms of leakage current, it is less.
you are going too much into the integrated device point of view. In general, I'm asking, uh, why is it that silicon has not found any replacement in the mainstream electronics?
So because in fabrication, the chemicals and high temperature, it can
Okay, so one thing I would again like to emphasize. So when we talk about fabrication, it is very very important to understand the entire context of the discussion. Okay, so silicon has been sort of invincible till date and will continue to. Why? Because of the four or five basic processes. Have you studied about or heard about VLSI processes? Fabrication processes. Fabrication process includes oxidation, patterning, that is photolithography, oxidation, then you have ion implantation, and you have silicidation, and metallization, and what else? Anything else I'm missing out? Etching. Okay, so these etching, oxidation, photolithography, and ion implantation. So these are the basic processes. And if you it is lot more interesting to study entire electronics when you are studying the theory. We tend to focus more on theory. But if you keep the perspective of fabrication along with theory and see how the things are actually fabricated also, you will get much more insight as to why a particular material system has been chosen. Why this? Why not that? So that is a very interesting part. So it is these 4 5 processes, that has led to one of the biggest miracle, and that is, the modern day technology. Because Moore's law essentially we were able to follow, because over the time we have been, our lithographic setup has been able to also follow the scaling down trend. So we started with doing the lithography in the roughly in the green region. We then moved on to blue region, then UV region, then near UV, then now extreme UV, and finally we go to ion beam or X-ray lithography. Okay, so the reason is because this patterning, we will use mask, right? And the mask and the patterning, if we want to develop some pattern on the substrate, um, the process by which this happens is basically, I will illuminate it by a certain beam of light, especially when it is photolithography. So in that case, the pattern that I am able to successfully transfer will be limited by the diffraction limit, okay, and which will be limited by the wavelength of the light used. So the entire aspect is that you simultaneously go on reducing the wavelength of light, and that has happened in the past, and that is how miniaturization trend has continued for close to 5 to 6 decades now. Okay, and the other biggest advantage of these processes is combination of these processes, one after the other, can give rise to your 3D integrated structures over the substrate, and that has led to what we call as very large scale integrated circuits. So unless VLSI, so even if I am able to show carbon nanotube based transistor is better than my silicon transistor for some kind of application, where is the integration of carbon nanotube? How will you integrate a carbon nanotube based transistor over large area? to realize the same level of functionality which silicon is able to do. So that is the biggest challenge. Okay, so it's the VLSI which is the key enabler of all this and has been at the hem of the affairs. So basically, we have to understand, so if I am developing just a sensor, certainly if I have a high mobility material, that is a better replacement for silicon. So I can go for a high mobility material. Now, if I am developing a sensor which has to be implanted inside human body, I have to look for a material which is biocompatible. Okay, if I have to, I'm developing a sensor which has to go into space related applications, then I have to think about something that can sustain high temperature. So again, depending on what application we are putting in our device, we have to come up with different, and that's where the material research actually stands as of today. But till date, silicon has not been replaced. Now, in these organic materials, since it is difficult to have that kind of 3D integration because these materials are soft and you cannot subject them to some kind of chemical agents and things like that, and the different stages and especially the oxidation. Oxidation usually happens at 1200, 1500 degrees Celsius temperatures. Though at those temperatures, these materials, because organic materials can sustain, most of the organic materials cannot sustain temperatures above 200, 250, 300 degrees Celsius at the max. Okay, because most of these materials, their glass transition temperature is around between ranging between 200 to 300. So basically, glass transition temperature means they will go into some kind of molten state. So my thin film will become more of a, and I will end up destroying whatever I have coated even. So I have to ensure that none of my process stages are having high temperature. So that is where, thanks to soft lithography. So soft lithography talks of another approach, and in fact has been well used. And in fact, what it talks about, I will just tell you first that. So instead of using, so we first develop a master. Okay, so first time the master can be developed using you can go to any level of this feature size, because if you use X-ray or E-beam lithography and develop a master, you will be able to develop any feature size, because technically electron beam and X-ray beam have much smaller wavelength and are suitable for any kind of any resolution. So you can go for low resolution, you can develop a master. Once you have developed a master, you code PDMS. PDMS is a very nice elastomeric material. You can coat this over the master, and then what happens is when it settles down, it will take the entire, this entire shape will get transferred. And this becomes your mold. You can then take it out. This becomes your mold, and on this mold you can then coat some materials. For example, as you can see here, PDMS is it is coated with certain material, and then we can. So this mold is sort of used as a um, what do we call some kind of print, just like you have a head in the printer, so similar to like that. So basically it can be used to transfer certain material. So these surfaces can be functionalized. So first you can dip it into certain material, and then you can coat it on the substrate. So like that, this can be done repetitively. So first time one mask you need to make using X-ray or EV lithography, but once done, or photolithography, but once done, it can be used in a repetitive manner to perform this kind of patterning. So that is what is soft lithography basically. And these are the different, you can go into more details of it about the soft lithography, but just to give you an idea. So you have micro contact printing, micro transfer molding, micro molding in capillaries, and solvent assisted micro molding. So these are different types of soft lithographies that are possible. Then finally I come to vacuum based thermal evaporation, or this vacuum sublimation which I talked about. So vacuum sublimation, as I said, you have a chamber. The chamber is taken to a low pressure of 10 to the power minus 5 bar, And you have the material, organic material, which are typically small molecules which can only be evaporated. And what we do is by means of a resistive heating approach. So we have a coil, and this is being placed in a crucible, and we have a coil by means of which we heat this crucible. And if the temperature is reaching near its melting point, so the material begins to evaporate, and it begins to deposit onto the. So typically the substrate is held in a inverted configuration over here. So the material, and in fact this kind of approach is also used for deposition of metals also, by using what we call as the thermal evaporation technique. So this is very similar to that thermal evaporation technique, and thickness of the film can be monitored by means of crystal microbalance. So this is vacuum thermal evaporation. And with that, I just come towards the end of it. So basically, in this part of the section, we learned about different coating techniques that are possible to develop thin films of these materials. Now I'll just discuss briefly about the charge carrier transport that happens in these materials. So again, compared to the conventional materials, what we see is the electrons or the charge carriers in these materials are actually localized. Okay, and this is the potential energy variation. So they are actually localized, and what happens is these lattice vibrations that are taking place actually assist in moving these because of this lattice vibration. It's like you have a pebble placed and you have a lot of troughs and I mean hills and valleys on a piece of cloth or something, and you have some pebbles placed, and because this let's say cloth is itself vibrating a little bit, my pebble gets transferred to some new position. So it is similar to that. So basically, it's the lattice vibration that helps in actually transfer of charge carriers from one molecule to the other, and that is what is the essence of charge carrier transport in these materials. If you compare with respect to the conventional materials, in conventional materials like silicon or several other semiconductors, mobility and temperature follow this kind of dependence. So mobility is typically one by it depends on n takes different values for different materials. So sometimes you will see one by t square kind of. So if n is two, it would be mu proportional one by t square. If n is one, it would be mu proportional one by t. So basically with temperature, but the bottom line is since it has a negative exponent on temperature, with temperature, mobility tends to decrease. So as we go for higher and higher temperature, mobility tends to decrease. Okay, why that is happening? So if temperature is low, my charge is actually able to move across more freely in the material. With the increase in temperature, lattice vibrations increase, and that lead to confinement of charge. So that is the case with the conventional semiconductors, and this typically is classified as the band type transport. On the other hand, if we look at the organic materials or organic semiconductors, in here, what is happening is, as I mentioned in the previous slide, lattice vibration is actually assisting this charge to, move from one point to the other. And in this case, what we call as polaron hopping. So polaron is basically the name given to the charge and the what should I call? So the organic molecule, they have certain structure. So the delocalization up of the charge up to the distance to which it is extending, that together is basically your referring to your polaron. Now, this charge carrier hopping is a thermally activated phenomena, and in this case, what we find is the mobility is actually proportional to exponential minus EA upon kT. So it is more of a thermally activated kind of process. So EA is the activation energy, and of course T is the temperature. So here you see mobility increases with increasing temperature, and that is one characteristic difference between inorganic semiconductors, most of the other kinds of semiconductors that you see, and these semiconductors. So basically over here, as my temperature increases, mobility tends to increase. Another important point we must bear in mind is these are sort of disordered materials. They are not perfect crystalline materials. So of course, in ordered materials, delocalization exists, but in disordered materials, the potential well, if we refer back to the basic model of how the bands are formed. So these potential well itself will have different values, and there would be some kind of delta V variation in the potential wells, and therefore that would lead to disorder in these materials, and which would eventually end up localizing my electrons in certain these potential wells, which are basically more deep. Okay, in order to for the charge to move on from one to the other, that's where the thermal activation is important. So we have this kind of hopping phenomena. So basically, in these materials, like okay, try to understand it like this. So if I have a charge carrier on one polymer chain and I have another polymer chain nearby, so by means of the thermal activation, my charge carrier can hop on from this polymer chain to the next one adjacent to it, and that is what we term as the Polar hopping model. And again, to give you again, I would refer to the amorphous versus crystalline discussion in the context of silicon. So, in the context of silicon, this is a typically density of states at the calculated at the valence band edge and conduction band edge. And as you can see here, this is the energy gap, and typically you will get this kind of dots, and these dots will be having a square kind of in the EK diagram. K square kind of dependency would be there. On the contrary, so this is if the material is single crystal. If the material is amorphous, this would extend a little bit more. So there would be more of localized states extending beyond this band edge. Okay, and that would be extending on both sides. And the situation in the case of organic semiconductors is also very similar to that of amorphous silicon. And besides that, of course, the hopping transport can also be understood like this. So you have different energy levels with respect to different molecules, and the transport actually of the charge carrier actually takes place from this to this to this. And usually, of course, and that's where the lattice vibrations and the temperature plays an important role. So in case this transition, if you see from here to here, this is a very big transition in terms of energy. So this cannot happen without extra energy being provided. So and that extra energy comes from the lattice vibrations. So typically this is what refers to as a hopping kind of charge carrier transport, and this is the empirical relationship between a charge carrier hopping from ith to the jth energy level. Anyway, so basically hopping transport is one of the unique features of organic semiconductors, and in this kind of transport, mobility is dependent on charge carrier density, and it increases with increasing charge carrier density, and it also increases with increasing temperature. So these two attributes are very unique and clearly distinguish between what is hopping based charge transport and what is a band type charge transport. So if you want to actually study the charge transport happening in these materials, you can do some kind of basic experiments to validate this hopping based charge transport. But at the bottom line of it will be that if you plot a graph between mu and temperature, it will follow this kind of relationship, and that will prove that these materials are going to follow charge carrier hopping. So And this is another disorder model which is often used to explain how the charge carrier transport happens. I'll again not go into the details of it, but what is important here is that the overall mobility is basically so this factor sigma is the width of energetic disorder, and then this one, this summation sign is referring to positional disorder. So if this is energetic disorder, positional disorder, and this term is taking care of both these things. And if you see, the mobility typically follows some kind of square root dependence on the electric field. Okay, so and it is also dependent on the magnitude of electric field. That is another very important. So basically, if I put all of these things together, one thing I see in these materials, mobility would be, of course, following some kind of relation, some kind of temperature dependence as well as electric field dependence. And in case if this energetic disorder is more than positional disorder, then the coefficient of electric field dependence will be positive. If energetic disorder is less than positional disorder, this coefficient would come out to be negative. So that has its own implications. Anyway, this is just to give you an idea what kind of charge transport happens. Now, finally coming to the device part, which I would like to uh, you know, go into detail. So today we will be discussing about, so based on all these understandings, the photophysical properties or optoelectronic properties of these materials, the coating techniques that we have to coat these thin films of these materials, and finally the kind of charge transport that happens in these materials. We'll now like to look into the device applications. So I would first like to focus on organic field effect transistors. In fact, I will be today's talk is mainly focused on organic field effect transistors. Little bit I will talk about photodetectors as well. So, okay, this is the typical structure of organic field effect transistor. You have a source and a drain electrode, organic layer, dielectric layer, and a gate electrode. And typically, you apply gate bias, you apply drain source bias, and measure the current flowing in the circuit externally. And with that, you plot the IV characteristics of the device. Typically, you can plot the transfer characteristics between IDS and VGS, and output characteristics between IDS and VDS for different gate source voltages. And these are the different types of device configurations or geometries, so called. So you can have wide variety of geometries in this case. I'll tell you from where does this, why this is not possible in silicon and all that. But basically, you have total 4 possible combinations coming out. So if you have top gate, top contact. So basically, the gate is on the top. This is the insulating layer, and the semiconducting layer is here. And with respect to gate, if you see, so here the contacts are placed on top of the semiconductor film. That's why it is called as top gate, top contact. So basically, top contact and bottom contact structure. So in this case, for example, it is bottom contact. So top gate and or bottom contact or top contact structures. From this graph, it will be these two schematics. It will be more clear. So the only difference between these two is, in this case, source drain electrodes, patterned source drain electrodes are deposited before depositing the semiconductor layer, and in that case, semiconductor layer is deposited first, and then source drain electrodes are patterned source drain electrodes are deposited using shadow mask technique. So that is how the difference is. Okay, so you can have all these 4 types of structure. In this case, the gate is at the bottom. In this case, gate is on the top. Okay, it's an inverted device structure. So that is the different types of device configurations that exist. And typically, you will have these kind of, you know, the transfer. So this is the transfer characteristics, and these are the output characteristics of the transistor. Now let us look into the some of the basic assumptions while deriving IV equation for an OFET. So one basic assumption is mobility of the charge carriers in the channel is constant. We also assume that the gate capacitance is constant and independent of gate voltage. and the source and drain for ohmic contact to the semiconductor. So unless all these conditions are met, you will not end up realizing the FET-like characteristics. And the charge density is typically N naught. The insulator thickness is much smaller than the channel length. Now let us look at the uh, okay. So here you can see output characteristics, that is IDS versus VDS for different values of VGS. Okay, and as you are probably aware, in this part of the graph it is a linear region, and then here it is sort of, and this parabola actually segregates the triode region and the saturation region. So this part over here is mostly, so on this side of this parabolic curve is mostly the saturation region. So transistor can be biased appropriately into any one of these regions based on, again, what we are intending to do with the transistor. You can use it as a switch, you can use it as an amplifier. So depending on that, you will appropriately bias it and use it. Okay. And okay, so of course, I guess all of you are sort of aware that it is the pinch off, that leads to saturation of the drain current. So ideally, this drain current goes on increasing with the drain source voltage, but beyond a certain point, it shows some kind of saturation, and that saturation is happening because of this effect called pinch off. Okay. Now, let us look at the transfer characteristics of OPEC. Okay, so I will first show you, for example, this is the IDS versus VGS curve. So as you can see, it shows this kind of behavior for VDS equal 3 volt, and for VDS equal 1 volt, it shows like this. Now this is a linear graph, let me tell you. And okay, so linear because the scale is linear here. But if we take log of these values, we end up getting a graph like this. So you see, this is a graph between root ID and VG in this side, and this is ln versus VG on this side. Okay, so by taking logarithm, basically, because on a linear scale, what happens is you are able to see only that part of the curve where the current is in large amount. But when small amount of current flows through, we are unable to, because that is all almost appears to be close to zero. So we are unable to see what is happening there. Okay, so that's where log ID versus VG graph is also equally important. So once you plot it log ID versus VG, the part which is almost appears to be zero is more magnified and properly comes out here, data points, and these data points correspond to this region. Okay, so we see the current changes by several orders of magnitude in this part of the bias regime. Okay, so of course there is some region for it, and basically from this graph also we can determine easily the threshold voltage. Threshold voltage can be determined from this graph, because once you have the saturation effect coming into play. So I will refer to the transistor equation. Then I will again over there I will explain how threshold voltage can be found out. But once you know the threshold voltage, basically this region is somewhat below threshold voltage region, and that's why this region is called sub-threshold region of conduction. So if you want to study the device, how does it conduct, and what is its behavior in the below the threshold voltage, so you must try to look into the sub-threshold conduction regime, and this is more of a sort of inversion region kind of. I mean, if we talk about with respect to the silicon counterpart. So inversion does not happen in this case. These transistors are mostly not depletion type but enhancement type. Okay. Now let me first take you through the gradual channel approximation. So The charge density NX, I think you can refer to some textbooks also to see what what these parameters are. But just a quick this thing. So you can write the overall charge density. This is the insulator capacitance, and DS is the thickness, and VG is the gate bias voltage, and VX is the voltage as we move from the source end towards the drain end at a distance x. And if we try to expand this, so we get ID equal ds in times W into Q mu p n naught plus delta nx into Ex, which is the electric field. Electric field can be written as minus del V by del x, and we substitute that, and we integrate this entire expression now, because you have a expression with respect to which relates basically current with respect to voltage. As we integrate, we end up getting this kind of expression. I think all of you are aware. So basically, I would like to emphasize on one point: gradual channel approximation makes one assumption, and that assumption is that the vertical electric field applied in the device is much larger in magnitude compared to the lateral field. Okay, and that usually is the case, because the lateral electric field is only meant to extract or inject charge carriers between source and drain, but essentially those charge carriers are induced by the gate bias that we apply on the gate electrode to create a sheet of charge carriers in the uh, insulator semiconductor at the interface of insulator and semiconductor. So basically, this is the equation, and from this equation, if you see, where Vt is the threshold voltage. In fact, please do not confuse with the thermal voltage. So this is, or if you want to put it, you put it as Vth. Okay, so this would be basically W is the width of the channel, L is the length of the channel, mu is the mobility, C is the capacitance per unit area of the capacitance, insulating capacitance, and Vd is of course the drain source voltage. So if you see in the saturation regime, what happens is Vd is Vgs minus Vt. If you substitute, you get this kind of relationship, and from here you can see that in the saturation regime, if you take a square root of this entire expression, then it would be square root Id is equal to and root of this entire thing into Vgs minus Vt. So if I plot a graph between square root Id and Vg, the intercept on the x-axis will give me Vt. So that is how in the previous slide, square root ID versus VG graph, and the linear portion, you extrapolate that and you find the threshold voltage. So that's how you find out from the data of the device, you find out the threshold voltage of the device. And threshold voltage is the that value of gate voltage at which the device turns on. Okay, so below threshold voltage it is assumed to be turned off, and above threshold voltage it is going into the on state. And then of course you can estimate mobility in both linear as well as saturation region. That's now I told you how to do that. So using this saturation region equation, you can estimate mobility in the saturation region, and linear region. Of course, the since in the linear region Vd will be very small, so Vd square by 2 can be neglected, and therefore this entire expression would be this multiplied by Vgs minus Vt into Vd, and that would be your current in the linear regime. And from that you can actually estimate the mobility in the linear regime. Now, okay, before I move further, I would like to talk about how much time do I have? I think time is already up. Okay, so um, can I take 10 minutes? Okay, so the one of the important aspects of once we understand the device, first of all, if you are new or a beginner in this kind of device as such, it is very important to find out what are all the challenges that are existing. Okay, because unless you know, so a good PhD or a good research it is not important to solve the problem. It is most important is to define the right kind of problem. A problem that is going to capture your energies for next 3, 4, 5 years, and should be good enough challenging problem is the most important thing. So if you frame the problem properly, of course, then solving it is the next part. So it is important to understand what are the challenges existing. So let me put it in simple terms. Of course, we would like to have higher mobility transistors, organic field effect transistors. The present day mobilities are good enough for these transistors to be used, and they are being put to use commercially. But of course, we would like to further improve upon their mobility. So one is at the material level, we would like to have improved mobilities. Another is, if you see, most of these organic field effect transistors tend to have higher contact resistance. And I'll talk about that. What is the reason for the origin of contact resistance? That is what this slide is. And then third is, we would also like to reduce the bias, the gate bias that we apply to these transistors, so that they can be operated at much lower bias voltages, and therefore we can build circuits and systems based on that. So typically the contact resistance in organic field effect transistors is essentially due to the source drain contacts that we are making to these devices. So the contact resistance actually manifests itself. I'll just show in the next slide. So it basically manifests itself in the form of the IV characteristics of the device, and it essentially emanates from the non-alignment of metal Fermi level with that of the semiconductor homo energy level. And also, you can also think of some kind of interfacial barrier that gets formed when we have this metal and organic interface. Okay, and in general, if I look at between the source and drain and the organic semiconductor, the total resistance that is there, so it can be thought of as two different components. One is the resistance in the channel region, and the other is the resistance appearing at the contact. And it is this contact resistance which is basically the resistance at the source end and at the drain end, which is basically your contact resistance. And how does it manifest itself? I'll come on to that part. But basically, if I look at it, for example, with respect to top contact, so this is the channel resistance, and these are the contact resistance in terms of, if I look at purely resistive model of the device. Okay, and typically, if this is the case, what I can think of, or what we can think of is basically, if I vary the channel length of the device, and I plot, and I calculate the total resistance. Total resistance can be calculated because I apply IV. I mean, I can measure the IV characteristics, and from that total resistance can be calculated. So if I plot a graph of total resistance versus the channel length, I would get typically a straight line. And when I extrapolate that straight line to zero channel length condition, typically zero channel length you will not get. But when I extrapolate this, so suppose I have got these points for different channel lengths, and then I see that it falls on a straight line, and then I extrapolate that straight line, the y-intercept gives me the contact resistance. So this is called transmission line method. It was pioneered by this group. This is the paper which you can refer to. Now, so that is basically the conventional, transmission line method. So your drain current is Vd upon R on, that is the resistance of the on-state resistance of the device when the device is in the on state. So which will be basically contact resistance plus the channel resistance, and channel resistance we will write it by this expression. And so basically we end up realizing that the on-state resistance is Vd upon Id, which is basically your total resistance is sum total of Rc plus L upon W into mu Ci Vg minus Vt. So this is the expression. Now, if you multiply with the width of the device all across, so this is called width normalized total resistance, width normalized contact resistance, and this is the channel. Now you see a graph of total resistance versus L. So these are all things constant. So if I plot a graph between this and this is the variable and this is the variable. So in that case, the intercept would be giving me contact resistance. So that was the approach adopted. This is the IEEE TEV paper, which have shown this approach. So in this approach, one important thing is VGS minus VT should be maintained at the same.